Huh? Flying clip, I think the microphone's on.
You can't, the green one is to one side, the big one. But it's not going to do anything. Not active. You can try, it's not hold it like this. Forward. Back. Up. Or just leave it. I don't know how you position it. Right here. Yeah.
That looks right up my nose.
Oh, what?
But it's coming right up my eye.
It don't move forward, down. Look at me, it's for me.
Yeah, I know. Just flipping that.
Now they send a message. I guess it should say that you dropped off the section. to go forward.
Go backwards.
No, this is to go forward. Next slide. Back. This is laser. No, the laser. Oh. Yeah, like this. Yeah? Don't forget this, the biggest one is to move one slide. Okay?
And that's to move backwards. And
To move backwards. No. Forward, red is back, and this is laser. Fireworks are laser.
maybe it's best if you don't like it.
Yeah. So you just come into the... I just don't know how you position it onto the movie bar. For your...
You could ask Jonathan.
Yeah, he's preparing his talk. So let's go down and we have to find Katrina.
Hello, everybody, and welcome to our next session, which is on gravity wave modeling and observations in the MTI. Our first speaker will be Jonathan Snively. For all speakers, Katrina Bossert here will be keeping time, and the speakers will have 8 minutes for their talk and then 2 minutes for a question afterwards. So without further ado, please welcome Jonathan Snively.
Thank you very much, Chris. So I'll do my best to work within 8 minutes here. My name is Jonathan Snively, and I'm pleased to present on modeling of acoustic and gravity wave interactions, coupling, and observables. And I'm pleased to also thank our team, which is even much larger than this because we have a bunch of observationalists and experimentalists working with us as well. This work is supported historically by NSF first, by NASA next for several great projects, and is currently under a DARPA cooperative agreement with the AMASENS program. We've been working to develop modeling capabilities as well as observational techniques, in particular for acoustic wave sensing within the typical geophysics data here. So this particular example, I'm going to start with an example rather than the details, is a case study that Roberto Sabatini presented at the AGU meeting. This is something we worked together on, and it is an example of a breaking acoustic gravity wave field, but also the propagation of a spectrum of acoustic waves that are launched by a series of explosion-like pulses. Now, the reason for this kind of simulation is because when you have sources that are generating acoustic waves of interest, and a really good example right now is the Hunga Tonga volcano that has captured a lot of attention because it generated acoustic gravity waves that really circled the globe, literally, and were able to be detected on sensors really everywhere. It is how those waves interact with the ambient environments. For example, how do those propagate through breaking gravity wave fields or other dynamics that are intervening? So looking at cases like this, we're starting here with a breaking wave field. And I have to say, if you have access to the file directly, you can see that there's more to the dynamic range here that's visible. The quantities visualized red and blue represent the pressure perturbations. You can see them at lower altitudes, but more prominently at higher altitudes. We use Mach numbers as a diagnostic of the acoustic and gravity wave field for this. So you're going to see two overlaid colors. And as we cycle through the different pulses, every, I believe, 180 or 200 seconds, we're launching an additional acoustic wave that has around a 10-second pulse length scale, and then it evolves due to steepening and propagation through the lower thermosphere. But as these propagate, you can see that it's being distorted by the gravity wave field. And if you want to track the wave fronts, you see the waves reaching into the thermosphere. This is 200-kilometer altitude, so you have waves that are passing into what would be the ionosphere if it was included in the simulation. And if you compare what's going on the left versus right, when you have this gravity wave disturbance, you have additional scattering of those acoustic waves. You have formation of trailing oscillations in the acoustic wave field. And on the other side, you have minimally disturbed acoustic waves like you would expect in an idealized simulation or some kind of a simplified model of propagation. Now, the reason this is interesting for us is because we want to make connections also to this wave field that's evolving in the thermosphere, because this is one of the key ways that we can detect acoustic and gravity waves that are in the thermosphere. So this is, for example, the kind of stuff that happens with earthquakes and other seismic events, tsunamis, et cetera, where you're going to have some kind of a transient input that is launching waves that propagate to high altitudes. So in this case, this is Paul Inchin's work for the New Zealand Kaikoura earthquake, and you have an acoustic wave field that's passing through the atmosphere. He has also considered the airco layers for this, but the primary focus was assessing features in the GNSS data that turned out to be additive to what was available in the seismic data. In other words, you could gain additional insight into the processes that were occurring in the earthquake, the timing of fault events, and that was represented then in the GNSS data. Other classic examples of acoustic and gravity waves that we're familiar with in the literature, the Nishioka et al. 2013 event, for example. You have an EF5 tornado, you have this very strong convection, you have generation of acoustic and gravity waves that propagate upward throughout the atmosphere and impact the ionosphere. Now, we also have a favorite event. This is what we refer to as the Iowa storm, but really it's nowhere near Iowa. It's just a series of Midwestern convective complexes that launch an absolutely incredible acoustic gravity wave field that's visible in the 630 nanometer airco imagery. This is presented by, has been presented previously by Chris and published, but we, of course, keep digging into this event with larger domains and relatively higher resolutions to make sure that we can still reproduce some of the key features of this as the model evolves. In other words, we want to make sure our simulations are increasing in fidelity, not decreasing in luck. So this is an example of what's seen in data. You have these gravity wave-driven TIDs, but you also have these acoustic oscillations, and these are important to represent in data sets because they provide extra insight into the short timescale evolutions of the lower atmosphere, basically. Are you radiating waves at higher frequencies too? You can see the same kind of thing in the simulations, fortunately. So when you look at the forcing from a simulated convection using NEXRAD radar data, Chris Heel and Paul Engine have identified acoustic wave onsets in the simulation that are well-timed with those in the data. And that's promising to say that we're scratching at the surface as to why these arise, and also the underlying features of the sources, in this case, basically just fast convection. So the kind of models we're using are the MAGIC model for acoustic gravity wave interactions and coupling, which is something that my group has developed over the years, and as well Matt Zettergren's Gemini model, the geospace environment model for ion-neutral interactions. We've been adapting these literally in the Forest Claw framework for adaptive mesh refinement. Now, MAGIC has been running this for a little bit in various testbed capacities, but we've been securing much greater performance in recent updates to this, and now Gemini as well is being incorporated into a Forest Claw framework. And this uses pForest as the underlying mesh management, and then Forest Claw serves as the solver framework for the cell-centered finite volume methods that we use. But in the 3D extension, we currently are working with a formulation that is called an extruded mesh, which is basically horizontal AMR with a fixed vertical grid, and that's a useful approach, especially for the ionosphere. For the atmosphere, though, we can leverage a full 3D AMR to get much higher performance in the future with gains similar to what we see in the 2D. You can possibly find my AGU poster somewhere if you want some more details of that. But looking at what the 2D looks like and what 3D would look like in a cross-section for 3D AMRs, you can keep thinning the mesh at higher altitudes. And this is really key because you don't need high resolution in the thermosphere. And since it's highly viscous, that ends up being a substantial extra computational cost. You end up with 5 times as many cells as you really need. But you also need lots of iterations or an implicit method to converge your viscous solution at those altitudes. So in this case, we are basically reducing the resolution so that we can also decrease the computational cost of the solution. And this ends up with about a 200x speed up so that these kinds of simulations in 2D run on a basic laptop overnight. That's a big improvement from before. And it shows promise to be able to run full 3D simulations in a reasonable period of time, even up to 100-meter resolution in the mesopause. So the 3D extruded mesh is, under, how do I go back? Can I do it? I can. Okay. We'll just look at this one and skip the little video here. The 3D extruded mesh is basically fully compatible with the existing version of MAGIC 3D, and this is just an example of a breaking gravity wave packet with impacts on the hydroxyl layer, which is this purple layer. This is at a fixed altitude, so you can see a little more features than you would in an integrated context, but this resolution ranges from 1 kilometer to 4 kilometer, depending on the region. And this is, again, a simulation that kind of runs on a desktop computer in a 24 or so hour period, just for diagnostic purposes, but it has the same kind of features as the 2D simulations we showed before, but in 3D. So you can see the curvature of the fronts generated by an isolated source, and then you see the self-acceleration and braking and formation of turbulent structures within. I think I'm probably out of time there. I hope that's 8 minutes and not 10. Okay, cool. So the next step, of course, is to merge this with Matt Zettergren's Gemini, and he's reformulated Gemini into a sort of library-like interface, and this is now being embedded. It currently runs within Forest Claw, but not fully controlled by Forest Claw, and that's a really important next step. And we have computational scientists, Donna Calhoun and Karsten Burstad, who are working with us to create the communications architecture that works from MAGIC to Gemini, so we can very, very quickly communicate data between these and analyze that data at the same time. For example, if you want to do GNSS total electron content within the model as it evolves at a relatively fast cadence, that's going to be necessary rather than outputting huge amounts of data. So this is a continued work in progress, and we hope it'll have impact for a number of problems outside just the hazard acoustic waves and gravity wave scenarios. There's lots of normal applications as well that are more familiar than these specific cases, and those will hopefully be developed in the future through subsequent efforts. But we're looking forward to having a much better grasp on how we use the ionosphere and upper atmosphere to diagnose these high-frequency waves and hopefully the underlying processes. So thank you very much. I'm sorry that I'm pushing the edge of the time limit here.
Do we have any questions at all? Time for one question? Erda?
Good morning. I have multiple questions, but just one of them. We
Okay.
can talk offline, of course.
Okay.
In your MAGIC modeling,
Yeah.
do you how do you quantify the sources? Not only from specific events, but in general?
Yeah, so that's a really great question. The sources are, in some of these cases, a boundary input. So if you have a seismic event, we prescribe a boundary condition that mimics the motion of the Earth's surface from a seismic wave model. Paul Winchen has worked on that extensively. The other sources for convection are modeled by a technique by Stefan and Alexander that Chris Heal has presented before, and it's basically a volumetric latent heating that's described by a 2D map of radar parameters that's then translated to a time-dependent 3D map of inputs to the lower atmosphere. But this is entirely flexible. We can do inputs in mass, momentum, and energy, or we could apply boundary conditions. And we'll hope to have more flexibility and generality for other users in the future. All these codes are destined for open source. So we'll have to hopefully do a good job at documenting some of the details. But again, it's more of an experimental framework to conduct an experiment, a simulation, rather than to do forecasting, because they're relatively higher overhead than models that you would use for forecasting at this time. So that helps a little bit. But yeah, thank you very much.
Okay, I think we'll have to move on from there. Thank you for your questions. Our next speaker is Jaime Aguilar Guerrero.
That is the last slide. Let me go to the first one. Oh, thank you. Hello. I'd like to talk to you about some of my work related to simulation of observables. So for 3D model outputs for Gemini, a MAGIC is a good segue from the previous one. All right, so the driving question for this particular work is how to more and more accurately interpret our observational and model volumetric data, either for validation, interpretation, dissemination, and interfacing assimilation with other systems. This is pretty much a system science perspective, employing multi-sensor observations and modeling, and I want to point out three particular issues that I try to address here. The issue of observability of scales and three-dimensional structures, map projections, and observation capabilities for imaging instruments. I will use a specific case study to address these discussion points. We saw this before. Chris presented this on Tuesday. I won't cover much detail, so please focus on the images as I go through these slides. I'm showing here the results from Chris. And next up, we have some of the 3D structures that I have modeled for this. This is a larger domain than his original 2019 paper. Let's just see if we can zoom in here. Here I'm showing the positive green and negative pink perturbations for the OH31 airglow, shown on a 10:1 vertical to horizontal ratio to enhance the appearance of vertical structures. Now, these are two order of magnitude smaller airglow perturbations. This is the simulated CO2 radiance, and this is the temperature of plus 10 Kelvin at 1:1 ratio. You see the entire domain here from 0 to 300 kilometers. The latest simulation runs are a much larger domain, 3,200 kilometers by 3,200 kilometers. This high-resolution temperature render clearly shows the morphology of the acoustic signatures, the large bubbles that appear all the way to the top of the domain at 300 kilometers. This is very important to understand in the context of line-of-sight, mesospheric, and ionospheric observations where significant enhancement occurs when imaging through the angles of these very large wavefronts. Here is the high-resolution simulation, there you go, of the CO2 brightness temperature, and you can see detail of the smaller scale activity as well as the spiral structure here that is really hard to see on 2D slices of data. This is just a video of this. Here, this is a full picture of this all put together. We got an orthographic, We got an orthographic and perspective projections. If I may go back. Can't go back. Yeah, okay, there you go. All right, so this is one way of putting everything together. We have both our data, real data, perspective simulations, and just the raw orthographic simulations, as well as a sketch. So this is how I would try to explain this whole event in one picture. Now, for the next one, just a quick reminder of what is perspective view. Basically, it's simulating what a satellite would be, or also what an observer on the ground. This is what a person would see 800 kilometers away from this. Now, let's quickly talk about map projections and why I think it's important to be aware of this. Quick overview, there are three main types of map projections: conformal, which is shape-preserving, equal area, and equidistant. Here is just an example with azimuthal projections. What I try to convey here is that for local, regional, global plots, we must choose what is the most important quality of our data to represent. Is it the comparative area that's important, such as hotspots? Is it equidistant or shape preservation? Here I'm just trying to convey the idea that each projection has specific mathematical description that we can use to quantify distortion away from our choice of origin or map parallels. Perhaps these plots here present more clearly the idea of distortions for these Mach wavefronts and how their zonal meridional components can be greatly distorted. Here are more comparisons with magic outputs for an ideal concentric wave. Here's another one with just a linear case replicated along the latitude. Long story short, we need to think about the best and more accurate way to do this. Here are four examples. First one on the right, we decide to preserve first one on the left. We decide to preserve distances over longitudes. Next over, we preserve distances over latitudes. Next is where we preserve the direction of the gravity along geodesics on the ellipsoid that represents the Earth. And finally, the loximuthal projection, which is the one that I propose as a reasonable compromise. Here is a comparison of the loximuthal and the mnemonic projection. The mnemonic projection is the one where you use great circles. By choosing the loximuthal projection, we are aligning the x direction to the parallels and the y to the meridians, which lines up well with how we input wind data and allows us to use wave analysis in the same manner. And this is just with magic outputs showing the distortions. This is another graph that to show that we can quantify the distortions. Finally, I'm just gonna do a quick overview of how I'm studying the impacts of line-of-sight effects. Here we have 5 images placed around the US observing the exact same data from the case study. This is just how it looks, the raw synthetic images. This is them unwarped and extracted at the same coordinates. This is their corresponding periodograms showing their spectral content. Now, we can also do this for pointing images. So you can see here the geometry in this sketch, how we are actually pointing them now, not just looking at zenith. And this is how they look unwarped. This is how it looks the raw synthetic image. Again, if you actually take a closer look, you're going to see the loss of the filtering of scales here. And we quantify that with the periodogram. And actually, we can take this further, and I created 2 tracks here. Where I'm just going to place Mach imagers along these 2 tracks. And here I show their field of view just to show that they all are imaging the same area in the center. And then what I can do is I can take the total spectral power to see how it changes. One of the tracks was aligned with the wavefronts of one of the concentric waves onset by the thunderstorm, and the other one was anti-aligned. So by quantifying the total spectral power, we can see that the one that was aligned with wavefronts actually has more variability than the other one. And this is purely to the lines of size effects because the total intensity of photons is actually not changing much between them. And finally, I'd like to show some preliminary work that I've been doing with the Mango red lines using Magic Gemini. And the reason why I'm not showing this more in detail is because we see that the neutral dynamics play an important role. So the structures we see are not really aligned with the Mango data. You can see that here. So this will be the comparison with the Mango data, and this is the red line that I've simulated. This does not have like I said, the neutral dynamics. However, the structures in the temperature field from Magic actually do match up in scales pretty well, and this is what Christopher Heel has shown. So this is a work in progress. And as final remarks, I just want to say that I'm surprised at the amount of talk I've heard here in the CEDAR about the importance of visualizations. Now, obviously, of course, I think that is important from what I've shown here. And I also believe that we can use better visualizations for more accurate scientific students, not just for the presentation itself. Thank you.
Very much, Jaime. We have a question from Sharon here.
If you go back one slide, oh, shoot. Go back one slide, and I'm just wondering what the bottom right corner, you said that was one simulation, and then the left one was Chris Seal's simulation. I'm just wondering what the difference is between those two.
This is the Mango data?
Yeah.
Yep.
And what is the bottom right?
This is Magic coupled with Gemini.
Okay.
However, this coupling so far does not have the neutral dynamics, so this is MSIS for neutrals. And we see that there is just no clear comparison here in the scales. So what we think is the neutrals are actually playing an important role, so we need that information from Magic, and that is being worked on.
Is the box size for Magic thousands of kilometers? Or?
Yes. Now, the box size is pretty big, and this is the actual domain of Gemini here, and the Magic box is actually a little bit larger than this. Yes.
I think we have time for one more question if everyone has any. No? Okay. Thank you very much, Jaime. Our next speaker will be Erin Lay.
Do we have the slides? There we go. Okay. I am Erin Lay from Los Alamos National Lab, and I'm going to be presenting a technique to probe the D region that I've developed with Emily Hudson, who had a nice poster yesterday, and Xuanmen Xiao, my colleague at Los Alamos. And we are doing this work as part of the Airwaves project to provide some validation measurements in the D region, which are very difficult to get. So this technique, Xuanmen Xiao and I actually developed several years ago. And what we do is we use LF and VLF waveforms detected at a lightning receiving station. So they're lightning waveforms. And the receiving station detects a ground wave that propagates directly from the lightning to the receiver. And then it also detects the reflected ionospheric wave that comes a bit later. And let's see. The two parameters here that I want you to look at is there's the time delay based on between the ground wave and the ionospheric reflection, and that tells us about the height of the D region. And then there is what we call the peak ratio, between the amplitude of the ground wave and the amplitude of the ionospheric reflection. And that tells us about the steepness of the ionospheric profile. So we developed this technique using what's called the Los Alamos Spheric Array, which was a localized lightning detection network in the US Great Plains. The goal here is to extend this technique globally and to be able to provide D region measurements more recently for comparisons to different studies that are going on now. So we're going to use the Earth Network's Total Lightning Network, ENTLN. Now, the reason I have chosen this network is it has thousands of stations around the world. This map here shows the lightning receiving stations that ENTLN has. And then the other requirements are it needs to locate lightning and it needs to save the waveforms of the lightning. So ENTLN is able to do all these things. Now, because it is such a huge network, it has some compression algorithms that it applies to the waveform data. So pulling out the details that we're looking for is a little bit more difficult. But I'm going to demonstrate here that I think we've managed to do this properly. So this is just an example provided by Emily. And what we do is what it's showing is a small region that we choose all the lightning in that region in a small period of time detected by several stations. This is in Australia. And this shows you the waveforms, and we are looking at negative cloud-to-ground waveforms, so I've done a lot of work to get rid of all the other kinds of waveforms, because this particular type is the kind we've developed the technique for. And so you see that they're pretty consistent, but there's also a lot of noise in these waveforms in this small region. So what we do is we average together waveforms that are in a small box in a small time window. And so in this case, we used 5 degree latitude longitude by 10 minutes. And when you do that, you get, these are different waveforms in terms of distance from the station. So these ones are about 350 kilometers from the station, going up to 800 kilometers from the station. And this is very consistent with the modeling that we've done. So this is showing that this technique is working with the Earth Network's data. And now I am just going to demonstrate this technique using the Hunga Tunga eruption. I will say that this is the first, we've just got this working, and probably this is not the best scenario to demonstrate a technique, given that it's a extreme event, but everyone's very interested in Hunga Tunga, so I thought I'd take a look at it. And Emily had done some initial data analysis, so this was a good one to tackle first. So what we started looking at was data in Australia, so we need a lightning storm. So this particular plot shows lightning on the day of the Hunga Tunga eruption, and the red dots show the ENTLN Australian stations. Now again, I'm gonna show you averaged waveforms in 0.5 by 0.5 latitude longitude bins. I think I might have had that incorrect on the previous slide. And I used the technique that we published in this paper several years ago to find the best fit D-region ionospheric profile. So we assume an exponential profile on the bottom of the ionosphere, and it has two parameters. One is a height, and one is a steepness. So what we did in that previous paper to demonstrate the technique is we model the space of the height of the ionosphere versus the steepness of the ionosphere. And each of those gives us a waveform, like this red one, that we can determine the time delay and the peak ratio. And so this top plot shows the space that's covered by the modeled waveform and the difference between the modeled waveform and the measured waveform for the time delay. And then this one shows the same thing but for the peak ratio. But what we learned is that we have to put these two pieces of information together because the time delay is more directly related to the height of the ionosphere, and the peak ratio is more directly related to the steepness. So when you put these together, you can get a best fit contour plot where you find the parameters that best fit the measured waveform. So for this example, it's the best fit for this waveform that was 777 kilometers from the station. And then this example shows the same thing, but for a waveform that was measured 540 kilometers. So basically, we get ionospheric parameters in these cases. Now, let's see if this plays. Yeah. So what I've done is I've plotted those two parameters, the height and the steepness, measured with these in these cells over time. Now, the darker colors represent more nighttime-like ionospheres, and the lighter colors represent more daylight-like ionospheres. So we can see that we're getting reasonable results, and as the nighttime comes through, you get heights that represent nighttime ionospheres, and you get some steepness. The steepness bar here is the cutoff's not like exactly where nighttime would begin, so it's not as easy to look at this particular plot to see nighttime versus daytime. Now I plotted these same parameters versus time, UT time, of the day of the Hungatunga eruption, and the distance from the Hungatunga eruption. The two dotted lines are about 300 meters per second time of propagation from the eruption for two different eruption times. Now, what we can see here is that this technique definitely gives us the general shape of the ionosphere. The nighttime is this shaded region here. What I'm not quite so sure about yet is if this information can tell us about the disturbance due to the Hungatunga eruption. People really have not looked at the D region in this way, so I have to do more work on this. And like I said, we probably should have used started with a not extreme event, and so we're going to work on that so we can compare a not extreme event to this extreme event day. And that is what I have. So I think we've demonstrated that this technique is viable for measuring the D region around the world where there's lightning storms. And we'll have to keep working to see whether it can tell us about these extreme events in terms of TIDs in the D region. So thank you.
Thank you very much, Erin. I think we have time for one question.
Really great talk. I was just wondering, so you're using the kind of classic beta H type parameterized D region.
Yes.
Have you tried like data assimilation-like approaches, or is there just not enough degrees of freedom of measurement to work with to be able to do like a higher or a more or a larger set of parameters for defining the D region structure?
There really are not very many D region measurements. I mean, globally, there's a lot of localized measurements in places where you have ionosons and ISRs, and there's some rocket measurements. But I don't think there are enough data at this point to do data assimilation.
Maybe we can talk later. But
Okay.
I was just more like using more kind of, I guess, is there more information available from the measurements that you have than the 2 degrees of freedom that you're currently trying to fit for as well?
I'm not sure what these ENTLN measurements there are, because they've compressed the waveforms, and I've had to uncompress them, and we lose some of the resolution, the frequency resolution. But with a dedicated sensor that could really detect fine frequency resolution, you might be able to get more out of it. But I'm trying to make use of the measurements that are already existing so that we can get some measurements right now.
Really exciting work. Thank you.
Thanks.
Thank you very much for your question. Okay, I think we'll have to move on there. Our next speaker will be Sharon Vadas.
How do you go backwards? Can you go back one slide to the first slide? Okay, so I'm going to be talking today about gravity waves in the mesosphere and thermosphere from mountain waves in the polar vortex, although I'm going to concentrate on the polar vortex because it's a fairly new source. I won't be touching on the Tonga case. I showed that the other day. Maybe, I think at AGU I'll touch on that. So sorry if I promised a few of you that I would. This involves a bunch of people. You can see the list there. In order to, so what motivated me to do this was I visited IAP a few years ago, and Gerd Baumgarten showed me his data over Alomar, northern Norway, and it had a ton of what I call fishbone structures in it, where there's clearly upward and downward going waves, and they happen all the time. And I thought, oh, cool. That's where the mountain waves from the Scandinavian mountains break, and I thought, that's pretty cool. That's probably secondary waves from mountain wave breaking, but I was absolutely wrong, and it took quite a bit of analysis and comparison with the model data for me to finally realize that these were actually the primary waves that were breaking were generated by the stratospheric polar vortex, and then they propagated westward up to where they broke. So the stratospheric polar vortex generated the waves, and those ones broke at around 60 degrees north, and then the secondary waves then propagated northwestward and went another 10 degrees north over Alomar. So anyway, this was what motivated the study. And you've probably all seen this, but when you deposit momentum from wave breaking into the atmosphere is accelerated horizontally and over a localized region in space and time, and the atmosphere is not happy being in this kind of a state, and so it radiates waves and also generates a mean counter-rotating cells in order to get back to a state that's not accelerated. So what I did was I asked Erich Becker to run his high MCM model, and this model now extends to 450. I think the resolution is a half a degree. You can resolve waves down to about 180, 200 kilometer horizontal wavelength, and it is nudged to the large scales that are extracted from MERA-2 up to 70 kilometer altitude. So MERA-2 goes to 70, and I think we taper it off so that it goes to 0 at 70. And it's only the large scales that are nudged. So any gravity waves that you see in the high MCM are generated naturally by the model. So there's the bottom boundary of the high MCM is at the ground, and it follows the terrain, which is gotten from a geological site. And so the wind that's over the mountains, that generates the mountain waves. Those are evolved naturally. And then if you have the stratospheric polar vortex, wherever you have shear in that background wind, that's where the waves that are present can extract energy from that shear. So the left column shows the high MCM simulation on that same day and time. Here's T prime times exponential of minus z over 14 kilometer in order to scale out so that you can see the downward waves as equally as the upward waves. And here is the lighter data from Gerd Baumgarten. And here is where I've extracted out the fishbone structure by just retaining downward phases above what I call the knee and retaining upward phases below. And you can see that the agreement is quite good. So the high MCM is able to model this event really well. And then the question is, okay, what's happening? So now we're going to investigate the model in order to find that out. Before I do that, I did one more comparison with AIR's data. So this left column is the high MCM, and this middle column is taking the high MCM data and removing the waves that AIR's cannot see. So this is what AIR's would see. Based on all of these waves, it would just see these waves. And then here are the actual AIR's slices obtained by Katrina. And you can see that the agreement between the AIR's and the high MCM is quite good. These are the primary waves that are coming up and breaking and depositing their momentum and then creating the secondary waves that we then see in the Alomar. So, okay. So if you go then and analyze the high MCM, nudged high MCM data, you're looking for what are the waves that are breaking that create the body force that creates those secondary waves, and it's these waves here. And you can pin them down to the waves that are generated on the lower side of the polar vortex. So here you have a huge eastward wind, and on the bottom side of the eastward wind, on the outer edge of the polar vortex, there's a huge shear. GUDZ is very, very large. And so any waves that are present there get amplified by that shear. What does that mean? It's mean flow gravity wave interaction. So the gravity wave amplitude grows and the shear is decreased. So basically the waves are able to extract energy from the background. And here you can see, this is the Mera-2 data right around the maximum of the polar vortex. And you can see that there's regions where the amplitudes are huge, and there's regions where they're smaller. And so the polar vortex is not some beautiful, stable, circular ring on that day. Okay. So what we've done, so that's a paper that we just submitted. It's under review at JGR. And now we're looking at going higher, because I want to know what are the gravity waves in the thermosphere that result from this event. And so here's the polar vortex generated gravity waves. And here I've multiplied by T prime times rho to the 0.12. And I found that this number works well in order to see all of the waves at all of the heights. So if you plot square root of rho, which is an energy conserving thing, you see nothing at the higher heights. And that's because when you have multi-step vertical coupling, every time you have momentum deposition and re-excitation of waves, the waves that are re-excited come in at amplitudes that are 5-10 times smaller, and then they grow exponentially, and then they're killed because of critical level or wave breaking, and then the amplitudes of the new waves are small, et cetera. So this ends up being a good factor to be able to put everything on the same plot. Okay, so here you have the gravity waves from the stratospheric polar vortex. Here are the secondary waves. Here's Alomar, that would be right here. So those are the secondary waves that GERD sees, and then you have tertiary waves, and it looks like a 4-step coupling process. It doesn't really matter how many steps it is, but what does matter is that these original primary waves are not the waves that you see in the thermosphere. And so the waves that you end up seeing in the thermosphere, they have much larger horizontal wavelengths, much larger vertical wavelengths, and importantly, much faster horizontal phase speeds. These waves move at about 40, 50 meters per second. These are moving at hundreds of meters per second. Okay, I'm running out of time. So here they are, and these are the waves from the polar vortex. They're propagating at noon. They're propagating this way. What's surprising and really interesting about these waves is they look like LSTIDs from the aurora, but this is a neutral model. There are no LSTIDs from the aurora in this model. So then you can go back and think about Nathan Frizzell. I saw him earlier. I don't know if he's here, but he wrote a paper in 2016 looking at super darn data, and he found that in general, the ones that he was looking at, the MSTIDs, were related to the polar vortex and not to geomagnetic activity. So I'll touch on that at the end. These are TEC plots that, DTEC plots that Larissa Goncharenko made for me, and here's the corresponding results from the high MCM, and this is as a function of latitude and time. And you can see that in general, the high MCM is able to capture the wave structure nicely. It's not getting everything. Obviously, it doesn't have an ionosphere, but it's getting most of the wave structures pretty well. And here's as a function of longitude. And again, you see some general features that are captured. And finally, this is at the highest latitudes where you would expect the polar vortex generated gravity waves to be the strongest, and you see some nice features in here. These waves are the higher order gravity waves from the polar vortex, and I believe we're seeing them in the TEC data. So, southward propagating waves at local time noon are not necessarily from the aurora. Takeaway. Okay. And I also compared the high MCM data with IceCat data during this case study, and you can see that the general features are very good. I'm out of time. I just want to read this statement from Nathan. I don't know if he's here. He wrote in his 2016 paper, in the local fall and winter seasons, the majority of MSTIDs propagated equatorward. He was in the northern hemisphere, by the way. No clear correlation with space weather activity could be identified. Rather, MSTID observations were found to have a strong correlation with polar vortex dynamics. Statistical analysis shows that MSTIDs are more likely during periods of strong vortex. Collectively, these observations suggest that polar atmospheric processes, rather than space weather activity, are primarily responsible for controlling the occurrence of high latitude and mid latitude winter daytime MSTIDs. So The conclusion is, number one, these waves are important in the ionosphere, and number two, you have to have a model that correctly deposits momentum and energy and re-radiates new sets of waves over and over again in order to calculate and model these waves effectively. Thank you very much.
Thank you very much, Sharon. I think we have time for one quick question, if anyone has. Marissa?
This is not a question, just a comment. I see there is a really large audience here. Yesterday, I presented more data analysis, specifically focusing on relationship to polar vortex and strength of wind. So we see this. What we see in TID data is very consistent with what Frisell was showing back in 2016, and we're analyzing several years of wintertime data. So it's a pretty consistent picture is emerging.
Is this a Millstone Hill, or is this TEC
No,
data?
TC data.
Over the United States, or where?
Europe, United States, we're trying to cover all the regions where we have TEC data. And I showed some, yesterday I presented some of it at another session.
All right, thank you very much, Sharon, and thank you for your question. Next up is Bjorn Kjellstrand.
All right, hello. My name is Bjorn Kjellstrand. I'm a postdoc at Arizona State University, and today I want to talk to you about ducted waves and a quasi-two-day wave over the Andes Lidar Observatory. I'd like to acknowledge a couple folks. Katrina Bossert has provided a lot of advice and help with this analysis. Steve Eckerman provided NavGem data. Jaime Aguilar Guerrero provided some projection code, and Alan Liu provided the ALO airglow data in the first place. And I've been doing this as part of the DARPA Atmospheric Airwaves team. All right, so basically we observe strong periodic features in the vertical winds that we derive from sodium LiDAR measurements that were captured over the Andes Lidar Observatory, located right here. These waves persist for hours. They don't travel vertically. The Chow et al. 2016 paper has shown that these are, in fact, ducted waves. At the same time, we observe waves propagating in the ALO airglow images. The propagation and direction of these waves varies with a period of 48 hours, and we believe that they're the same waves. So basically, our hypothesis is that the quasi-two-day wave is, in fact, what's causing this ducting. All right. So let's just dive into the ducted waves that we observe. So up top here, I've got 4 days, January 16th, 17th, 18th, and 19th, 16th, 17th, 18th, 19th, and we observe ducted waves in the sodium LiDAR-derived vertical winds. So this is the 2016 paper. They studied this extensively, showed it was a ducted wave, and we see a very similar signature on the 17th, 18th, although there is a bit of a complication already arising, something that's clearly not ducted and which clearly has some instability features, a bit of a foreshadowing there. And then on the 19th, we also see ducted waves across our entire vertical extent. For the full duration, and just for to kind of get our bearings, these are time periods that last something like 9 hours. We're looking between 80 to 100 kilometers altitude. These bottom 4 plots, I've done wavelet analysis for each of these. I just did an altitude-wise wavelets for all of them, took the mean of those. And I have in cyan shown the high power apparent in the wavelets during these periods of ducted waves. You can see that there is some complicated structure emerging already. Things are not monochromatic, and I'll get into that in a bit. But in general, we see waves with periods of something like 5 to 30 minutes, more typically 10 to 15 minutes. Great, so this prompted us to look at the airglow during this time. And here I've got 4 movies, which I don't know if they'll play, but that's fine. You can come to me afterwards. I'm happy to show these movies. There's 2 things that I really want to take away and you'll just have to believe me for a moment, which is that waves propagate upwards, downwards, downwards, north, south, with a 48-hour period, and we see wave structure. These are what we think are the waves that we see in the vertical winds measured by the LiDAR again. Okay. Can I go to the next slide? Perfect. Okay, so to convince ourselves that we are in fact seeing the quasi-two-day wave, we looked at the NavGem meridional winds. And this top plot I have here is a color plot of the meridional winds vertically over Cerro Pachon, the location of ALO. And indeed, we can see north winds, south winds, north winds, south winds. This is over the full 4-day period that I'm looking at. To kind of simplify that, I've taken a couple slices at 85 kilometers, 92 kilometers, and then I took the mean of everything between 80 and 100 kilometers, which is the region that we're probing with our measurements. And you can see, well, okay, there's some evidence of just daily tides. Things are a little more complex, but this sure looks like a sine wave with a 48-hour period. Furthermore, I've highlighted with this purple shading the time that I just noted on those previous slides when I'm seeing those ducted waves. And interestingly enough, we actually see the ducted waves, they appear to correspond pretty closely with the maxima and minimum of that quasi-two-day wave. All right, great. So we're very sure we see ducted waves. We're very sure we see the quasi-two-day wave. Can we draw a causal relationship between the two? So we think there is. To confirm this hypothesis, we essentially have to do two things. First, we need to find the vertical wavelength of these structures as a function of time and altitude, see that there's actually ducting there. And then second of all, we have to show this ducting is a result of the contribution of the quasi-two-day wave, of the background winds from the quasi-two-day wave. And this is where things get tricky. So we can quantify periods and horizontal wavelength from the airglow images. We can find background winds and temperatures from NavGem. We can also find temperatures from our LiDAR data. But in practice, we actually find evidence of widespread instabilities. Periods and wavelengths are wandering all over the place. They're constant in, they're not constant in time. Superposition is frequent. And furthermore, periods from the LiDAR vertical winds and the airglow measurements are correlated, but not strongly so. So to expand upon that last point, if we're going to compare vertical winds from the LiDAR and ALO airglow images, we better make sure that they tell us the same thing, right? We're probing the same part of the sky. We should be seeing the same signal. So to do that, I looked at kiograms. That's up top is, whoops, there we go. Up top is just a kilogram of the airglow data for that night. That's in black and white. I took a central slice. So it actually doesn't matter if I look at the horizontal or vertical kilogram, but the central slice makes physical sense because that is where the LiDAR beam is located. And then the bottom, I've done, again, a wavelet analysis of that slice. And then we have to compare this to the sodium LiDAR vertical winds. So here in blue and yellow, I have the wavelet analysis that I just showed you a couple slides ago. That is the LiDAR vertical winds, again, 16th, 17th, 18th, and 19th of January. On the bottom in red and black, I've got the kilograms for, I've got the wavelet analysis for the kilograms that I just showed you. And all of these plots are twinned in both Y, which is period, and X, which is time, UT. And what you can see is, there's some relations between I should say these cyan boxes are those same cyan boxes that I said, that I noted before. Those are the periods of high apparent ducted wave power. And you can see there's some relations. We see power in that same time and frequency domain. A lot of the time, we see some similar morphologies. We see, that as over a few hours, we see the period increase. On the 17th, we see kind of this consistent hum that is associated with that period on the 19th of large vertical extent, constant apparent ducted waves. We see that in both of these. But we see a lot of power outside of there, right? The kilogram wavelets do not match exactly the LiDAR wavelets. So that's complicated. Something interesting is going on. I have a few ideas why this might be, but that's a good question. Second of all, we're also having, it turns out that it's quite complicated to find the horizontal wavelength. I basically did a two-dimensional Fourier transform of the air glow images. We're only able to find statistically significant powers a few of the times. This red line shows just the top 3 of the powers. We also see harmonics that are apparently superimposed. We see the wavelength wandering with time. And then this is only less than an hour. We're not always able to get the horizontal wavelength. While we see waves, they vary quite a bit spatially. So my last slide. Just to summarize, we see clear evidence of ducted waves. We see horizontal with periods of 5 to 30 minutes, and we see horizontal wavelengths of 15 to 30 kilometers, somewhere around there. We see clear evidence of the quasi-two-day wave. Drawing a causal relationship is difficult, and this analysis is ongoing. Advice and suggestions are welcome. Thank you for your time.
Thank you very much, Bjorn. We have time for one question, if anyone has any. Oh, yep, we've got one.
Gets rid of a lot of your data, and you're using a narrow stripe. So that may make you much more sensitive to noise from small-scale structures going into the kilogram, whereas if you did a more analysis using the whole image, that may decrease the influence of small-scale structures. And kilograms are really useful for quick-look plots and such, but I really discourage their use for any kind of detailed analysis, just because you're getting rid of most of your data when you do it.
Sure, thanks for the suggestion. Well, we can talk offline since I know we have some time constraints, but thank you for the suggestion.
Thank you, Biff, and thank you, Bjorn. Our next speaker will be Mike Taylor, who will talk about the OR mission.
I've got to climb up onto this thing first. Hang on, the green one does. Well, good morning, everybody. It's my pleasure and delight to be here, back at CEDAR again after such a long time, it seems, and to see many old faces, but a lot of new young blood, and fantastic research. So I'm going to talk today, in the meantime of what I've been up to over the last couple of years, is basically working on a new instrument that we call the Atmospheric Waves Experiment. It's being built at Utah State University. It's supported by a NASA grant, and its capability is to be able to measure the waves that you've all been talking about this morning. Waves in the 30 to 300 kilometer range. Sorry, that helps, doesn't it? Waves in the 300 kilometers range, which really we now know carry lots of the energy and momentum, but we don't know anything more about them, it seems. We're doing individual events. Let me see if I get this right. I press the middle button. Okay. So I've carefully gone and forgotten to introduce my colleagues, but they'll let me off the hook. What I'm showing here is a beautiful movie made by Dave Sentman many years ago, showing gravity waves over New Mexico radiating outwards from a thunderstorm. This information contains all you need to know about the gravity wave, except how much energy does it have, how much momentum does it have. And that's a key data that we now need. It's okay to study the waves and say, yeah, it came from that spot, and we can go wave counting. But really we need to be able to study the momentum fluxes and their variability. So this mission and the OR mission is focused on getting at the heart of the energy of the waves and their distribution around the Earth. That's better. Okay. Well, we obviously, as being an NASA mission, you've got to have some objectives, but we have 3 very simple ones. First, obviously, is to try to measure with your instrument the properties of the wave, the wavelength, period, like we all do. And the next one is to, that's the top one, number 1 there. The second one is to study where the waves are going, how they're being enabled, essentially background wind effects, what's enabling them to get up there, and the third is what sources there are. Now, if you stay with that, essentially you end up with a fourth criteria where you come back again and say, what are the sources and their variability using other techniques? So if you look at that sort of chop through a banana or whatever, essentially we're looking at, it's just a sketch here, but you're seeing wave energy propagating upwards into the mesosphere and ionosphere. We're going to be looking at these waves in the mesospheric air glow, which is the darker of the blue layer between the sandwich there, if we want to describe it. But you can see, as the waves get up into that region, we're all talking about the waves breaking and depositing their energy, and then moving on to make secondary waves. So, okay, next slide. Here is our instrument, and also the method in which we do it. We developed an instrument called a mesospheric temperature mapper several years ago, and it turned out to be a delightful instrument that was capable of measuring winds and temperatures, not winds, temperatures and brightness. And I'll talk you through that in a second here. That's what's shown in that sketch. But essentially, it's going to be using data from the mesospheric air glow layers, and we were looking at the OH emission, which happens to be one of the brightest emissions in the infrared, and there are now infrared cameras out there on the market which make life very easy to get very high quality data with a simple infrared camera. So that sketch on the left there, I can, oops, which one's the, it's called, on the left there, marked airglow layer. That occurs at about 87 kilometers altitude. As the waves propagate upwards through the airglow layer, they cause variations which we can then detect with our camera. The next thing you've got, that's the middle one there, that's our camera. The next exercise is to turn that data into measurements of temperature and energy. And we do this because the OH emission has a very nice property. As the waves propagate through this, it creates variations in emission lines, P12, P14 background, each of which, the strength of each line depends upon its temperature. So this is an emission or a layer that you can look at with confidence, and it's been done for several years, many years. You can look at this and take the ratio of two of those emission lines there on the right-hand side and get a measure of relative temperature. But that relative temperature is really the rotational temperature at the airglow layer altitude. And that's been shown to be in thermodynamic equilibrium because of all the collisions. So measuring the rotational temperature with that simple ratio is going to give you a machine that enables you to make absolute temperature measurements just with your airglow camera. And that's what our temperature mapper does. Our temperature mapper that was made to fly on the ISS with our NASA campaign is called the AWE instrument, Atmospheric Waves Experiment. So they both use the same techniques. They're using different wavelength ranges on some parts, but otherwise it's the instrument that we're going to fly on the space station in 2023. You can see at the bottom left, okay, I'm seeing where I am on my numbers. See at the bottom left, it's a kilogram it was called, but nevertheless it's made from aircraft data or any airborne data or just temperature measurements with time. But essentially you let time flow by and you make and you just sum up the pictures and you end up getting a kilogram, which is this summary of nightfall data. And on the right-hand side there, you see a box which is an instantaneous image of our temperature data, and you can see the quality of the data. And that's our level 2 data product for our mission. And then on the left-hand side is the kilogram, which is made by summing together many of those individual waves. In the middle, I keep showing you this camera. That's just a sketch of the temperature mapper of the ore instrument. And it will be looking downwards at the aglo layer from the ISS at 414 kilometers. And we can do kilograms from that as well as straightforward imaging. And I'll just give you the, getting worried there. I need to go to the next slide. Anyway, you get the gist. Not seem to be. What am I doing wrong? It's the big one. Okay. Sorry, guys. It's been a while since I've done a few of these. Okay. So ISS, this is just general information. Summary down there below. You can see we take temperature maps every second as we're flying along with the spacecraft. I have difficulty seeing the thing. About 15 orbits per day. Well, you can read the thing. I don't want to put it quite like that, but you can read it better than me. My point is, it's a very well-equipped mission for us. Putting the temperature mapper on the ISS gives us all this information from day to day of the mission. The data will be stored. We have a data center at Utah State University, but it will be stored on the US data system, the space data system. So it's available to everybody. There we go. Just impressed. And this just gives you an idea of what we've got there. Essentially, between the plus and minus, the yellow lines, that's our field of coverage. It's about 54 degrees latitude. So we're covering a large part of the Earth. That's about 84% of the Earth's region. And it's going to cover essentially all the sources. You can think of convective sources, mountain wave sources. Think of another source, storms, we've had that, jets, all these things, anything that can make a wave or a source, we'll be able to measure in that range there and quantify. That's the key. We want to, this is a global mission. We can't do this all just with one instrument, so we've teamed up with several really ultra-high quality modelers, and you know them all, Jonathan here, Dave Fritz, Steve Eckerman, Hanley Liu. They all bring along a special model, Wacom, Magic, with Jonathan, and NavGem brings along the background winds so we can actually calculate the waves as they propagate upwards. So we're really armed there. So when we get the data, it'll be like a hot off the press, we can imagine, that we can turn these data into waves, and then those waves will be turned into energy and momentum flux. So we'll be expecting to be able to use these. And then you can go and study using this data available to you as part of the mission, essentially in your own light. Okay, let's move on. Here's an example from Hanley Liu Wacom X. So it's the best you can get. I mean, he's made a few others since then because they're always improving. But it's just showing what we expect to see when we sum all this up. And it's just hard for me to believe this. But soon we'll be able to, I mean, that's just, as I said, being done. I'll press it again. Oh, well. That cuts my talk shorter. I'm going to be on schedule. Okay. Let's talk about the instrument itself, the ore imager. You can see it there on the left-hand side. I've on purpose left it with not too much information. I wanted you just to grasp the thing. It looks like a Gatling gun, right? You have trouble taking that through customs. But nevertheless, you have several channels there. The whole instrument weighs about 50 kilos. It's pretty heavy. It's about 1 meter long, and the optics are f1, so it's some of the fastest optics you can make. And we have 64 lenses in the whole system for these 4 channels. We have built one engineering unit, which is what this is down there on the right, the engineering unit, and we're testing that in the labs at the Space Dynamics Lab as we speak. And this will also be doing cross-correlation measurements with our ground-based temperature mapper in the next few weeks. So we're going to be able to compare these things with the data from the Earth taken immediately, and also what we'd expect from models and from the other data, and cross-calibrating the 2 instruments. Okay. I'm pressing the big boy. There we go. There we go. Here we have another picture, just to put some scale size on the matter. There's the engineering model. The flight model is still being finished. It's yet to be calibrated, and but it's on track. So you'll be hearing more of us. Here we go. So this shows the timelines for the mission itself. It's been going for several years. You know, obviously with NASA missions, you have to go through lots of paperwork and lots of programs and reviews. We've gone through all of those. We've maybe 1 or 2 small ones left to do. And so we're now at the stage, if you look at the red writing at the top here, that we expect to be able to launch in the next year. And there's a possibility that that could be delayed a further several months because of programmatics with the SpaceX 29 rocket availability. Anyhow. So I said this was data was available for all. This is so we're showing that we're already embarking on that with the Embry Riddle correlations, collaborations with Jonathan Snively and his group, and our people at Utah State University. Basically, we're going to be able to give projects for these students, and we're hoping that as we're flying over your favorite observatory in southern Chile or whatever, we'll be taking some data, and you can dial it up and see what all saw. So it's really, it's a 2-year mission. So once it's up in on orbit on the ISS, it should be, I would say, well, the data will be archived, but we really look forward to a data burst of activity. And so we're building a high-quality data center to cope with this. So, as I say there, basically it's the atmospheric waves experiment, its first dedicated NASA mission, heliophysics. It's got firsts in all these things, and it's ready to help you all it sort of brings my dreams to come true after studying gravity waves for plenty of years, to be able to get on orbit and do the job. I'll stop there. Hope you can enjoy it.
I don't think we have any time for questions, but I'll encourage you to talk to Mike in the break if you have anything. Thank you very much, Mike. I appreciate that. Yep.
I only saw the 5, I didn't see the 8. Oh. So I apologize.
Oh, no worries, no worries at all. Okay, next up is Shuang Zhu. Thank you.
sorry. Okay, good morning, everyone. My name is Shuang Xu, graduate student from Hampton University. So today I would like to share something about thermospheric gravity waves above observed in GOCE. And I also want to acknowledge my advisors, Dr. Yue, Dr. Vadas, and Dr. Russell. And I also thank Dr. Hill for hosting this session. So here is the outline of my presentation today. The first part is some background or motivation. The second part is based on our latest publication. The third part will be what we are working at. The fourth part will be summary and directions for our future works. Okay, so, all right. So our motivation can be summarized by Train et al. 2018 paper about gravity wave hotspots at different altitude and seasons. So in this figure, it clearly shows that the missing gravity waves at around 90 kilometers altitude, so in southern hemisphere. So you can see over the southern Andes, there is a huge and well-known hotspot in the lower altitude, and then it disappears at around 90 kilometers altitude, and then it reappears at altitude of 250 kilometers and 400 kilometers. So we knew that one contribution of the missing gravity waves in the middle atmosphere is the residual circulations, but also we clearly see that one more very possible contribution of the missing gravity wave is the hotspot in the thermosphere. So the questions are, what is the mechanism that causes the variabilities in the thermosphere? And an even more difficult question is, what is the partition of missing gravity waves contribute to the mean flow circulation and the higher order waves, respectively? All right. So to answer this question, we use GOCE data to study the thermospheric variability. The GOCE measures the thermospheric density and cross-track wind at around 270 kilometers altitude in situ measurements. So firstly, we apply FFT analysis to decompose the satellite data, density data. We sort all the components with different wavelengths ranges into 3 lambda track ranges. The lambda track here means the horizontal wavelengths along the satellite track. And okay, so in the next step, we use KP index during satellite's lifetime of GOCE. So since the KP index and the density data along track are both time dependent, so we can also classify the aforementioned GOCE density observation perturbation by their corresponding KP levels. We can sort them into different KP levels. So by the way, all the processing steps aforementioned for GOCE density data was also applied to CHAMP data as well. So we can also derive the gravity wave hotspots at altitude of about 400 kilometers high. Okay, this is the climatology result of gravity wave hotspot distribution at global in the austral winter season from June to August, multiple years. So after the 2 steps, we calculate the standard deviation of filtered wave in each 5 by 5 degree map bins. So the result here shows the distribution of standard deviation TADs at 3 KP levels and all of the 3 lambda track ranges. So although we found that many interesting things when KP is high, for example, there is a, here. For example, over here, there is the clear aurora oval fingerprints in this subfigure, but let's just focus on the gravity wave distribution by extrapolation those results to absolutely quiet time with KP equals 0. Okay, so in the first subfigure, in the subfigure A, we can see that, excuse me, for all small-scale TADs, when KP is equal to 0, the hotspot over southern Andes is clearly seen. And in subfigure B and C, we can see that for middle and the large-scale TADs, when KP is 0, some hotspots are still over southern Andes region, although they are weaker and more diffusive compared to the first subfigure A. You may ask why we are excited about these observations. Well, for a long time, we assumed, but not fully confirmed, that the TAD hotspots over southern Andes and Antarctic Peninsula during quiet time are mainly caused by the remnant of geomagnetic activities. However, in this figure, we can see that the southern Andes hotspot is actually more obvious when KP is lower, which strongly suggests that those waves are mainly sourced from the lower atmosphere instead of the geomagnetic activities from the upper atmosphere. One more conclusion we can make is for the numerical models. As a comparison shown in the lowest panel, okay, those are the results from simulation from high MCM. They show that gravity wave hotspot distribution in thermosphere at 300 kilometers altitude, that is similar to the GOCE observation in many ways. According to Becker and Vadas 2020 paper, this high MCM, the high MCM is the only GCM that is able to model the temporally dependent deposition of momentum. And it is the only simulation that generate this gravity wave hotspot over southern Andes in quiet time. So we strongly suggest that in order to simulate the real mechanism to real thermosphere, the GCM should either take the multi-step gravity wave generation mechanism into account or change the current way of gravity wave parameterization radically. Okay, by the way, our 2021 paper also includes some climatology results from CHAMP data. So please check out our paper if you are interested in, but for the interest of time, we won't show here. Okay. Okay, I will wrap up very quickly. So there are also some limitations with our method in the paper that we need to improve. For example, from the beginning to the end, so far, we are analyzing the waves with certain different lambda track ranges, but they are not horizontal wavelengths lambda h. So to solve that problem, firstly, we have to replace FFT with wavelet analysis. Secondly, since the GOCE and the CHAMP only provide the cross-track wind perturbation, the full wind vectors perturbation, we have to find our own way to restore the possible full wind vectors and other intrinsic parameters. So the method we are using here is the gravity wave dissipative dispersion and polarization relations originally proposed by Sharon, by Dr. Sharon Vadas in her 2013 paper. So to be honest, we have a lot of results after this step, but I have no time to prepare them in slides in a very organized way. So anyway, this theory is very intricate but powerful. I'm still thinking about how to introduce it intuitively, but very lucky we have Sharon here in person. So if you are interested in this part, please reach out to her or to me. Okay. So I will stop here with summary for you, and welcome if you have any questions or comments and suggestions. Thank you.
Thank you very much, Shuang. We have time for one question. Erda? Yep.
Thanks indeed for this presentation. I think it's really valuable analysis for global modelers. And so I would be interested in looking at your data analysis and the global view of the gravity waves.
Mm-hmm.
And Trin's paper is absolutely fantastic, actually. The 2018 paper showing the maximum gravity wave activity at high latitudes in the upper atmosphere, thermosphere, depending on the altitude, of course. And I also would like to draw your attention to a high-resolution simulation study by Miyoshi et al., Miyoshi and co-authors in 2014, at 1.1 degree resolution only. However, even at that resolution, you can see a maximum gravity wave activity in the thermosphere at higher latitudes. So it seems like this is a very robust feature of gravity waves propagating from below and producing density and temperature fluctuations at those high latitudes. And earlier studies with coarse grid general circulation models using subgrid scale parameterizations have also shown these large scale features at high latitudes where you have enhanced gravity wave activity at quiet times. So all this comes all really nicely together, that it seems like in the thermosphere, in addition to all these high latitude energy and momentum sources, we have a meteorological, essentially, disturbances of meteorological origin. And we probably need dedicated missions to look at these high latitude regions, which we don't probably necessarily have right now. So the focus is, with the current missions, is more on the low latitudes and mid latitudes. So let's wish in the future that we can look at high latitudes in more detail.
Thank you so much.
Thank you very much. Thank you very much again, Shuang. Our next speaker will be Sophie Phillips. Oh, sure.
I just want to say that the simulations that Erdal is referring to, they don't have multi-scale vertical coupling, and I think it's extremely unrealistic during the wintertime sources. All of these waves have phase speeds less than 56 meters per second, and none of them can survive molecular viscosity above about 120, 130 kilometers. So I just want to have it on the record that I disagree that any of those primary waves can have any effect whatsoever at 400 kilometers or even 250 kilometers. So we'll just leave it out there as a point of contention.
Thank you, Sharon. Can we just take the discussion into the break afterwards in the interest of time, please? Thank you, Reda.
All right, cool. Hi, I'm Sophie Phillips. I'm a first-year PhD student at Arizona State, and I'll be presenting my research today from the troposphere to the thermosphere, tracking upward atmospheric wave propagation. And I'd like to thank my co-authors, as well as Lars Hoffman for the 3D AIRS data. All right. So a bit of background. As many of you probably know, gravity waves are important because they strongly influence the dynamics of our atmosphere. They do so in perturbing background winds, temperatures, and densities, as well as depositing energy and momentum into our atmosphere upon breaking. Vadas 2003 showed that secondary and higher order gravity waves arise from body forces due to primary gravity waves breaking. This means that gravity waves observations at a multitude of altitudes could really provide insight into coupling from below. And that's the motivation for my work today. I wanted to take a study of one night that had high variability and observe gravity wave propagation at different altitudes for that night. There we go. And now, in order to do that, I'm going to need a lot of instruments to look at all those different altitudes. So what I have here, first to look in the troposphere, I'm going to use MERIT-2 data, which goes from about 0 to 60 kilometers. I'm also going to use AIRS, a satellite that goes from about 200 to 60 kilometers. I'll also use the Rayleigh LiDAR from 40 to 80 kilometers at Poker Flat, the Meteor radar from 80 to 95 kilometers, also at Poker Flat, sodium LiDAR up to 110 kilometers, and finally the scanning Doppler imager in the red line that's also at Poker Flat will give me insight into the thermosphere. So in order to find a night that had high variance, I had to calculate the variances. In order to choose what days to calculate these variances, I'm interested in coupling from below, which means I was looking for magnetically quiet nights using a magnetometer reading. And I was left with these nights in which the LiDAR was running. And you can see here that December 23rd stood out as a day of high variance consistently when calculated for the temperature from AIRS and SDI, as well as the zonal wind for this red line. So I focused in on December 23rd, 2018. So to begin with the MERIT-2 data, which gives me insight into the lower altitude, there are two big takeaways that this plot shows, which is meridional and zonal winds against altitude. The first big thing to note is this change from positive to negative winds. Under these conditions, gravity waves dissipate and they're critically filtered out. The second big note from this plot is that at the lower altitudes, the background winds are very weak. They're not strong background winds. Keeping these two things in mind, I think that it's a fair assumption that any gravity waves that we see higher in the altitudes aren't going to be sourced from mountains because they'll be critically filtered out due to these background wind conditions. Moving upwards in altitude, we look at the AIRS data, and a significant perturbation is seen at about 165 longitude and 65 latitude north, at about 50 kilometers here. And it's significant because if you see on the temperature scale, it's to the order of 10 Kelvin, which is significant considering AIRS has a resolution of about 10 kilometers. Moving upwards once more with the Rayleigh LiDAR, you can see that waves are present throughout our period of measurements over this night. You can see lower in the atmosphere, too, there are smaller scale perturbations. In order to make it easier, I took a time slice at 10 UT and plotted it here on the right as a line plot. And you can see all these small scale perturbations lower in the atmosphere. And there's also traces of stronger, larger waves up higher in 55 kilometers. Moving upwards once more to the meteor radar, you can see that extremely strong zonal winds are present, both positive and negative, from 82 to 98 kilometers. And we see a similar pattern with the meridional winds as well, just not quite as strong. And stronger winds are also observed above these altitudes in the sodium LiDAR. The big takeaway from the sodium LiDAR observation here is that on this night there was a very strong semi-diurnal tide, here starting at around 8 UT and moving past the scope of the LiDAR at 16 UT. This could provide really interesting insight into future projects for the interactions between gravity waves and the semi-diurnal tide. And finally, we get to the thermosphere, where I use the SDI redline data to take a look at the wind speeds in this altitude. And what I did is I plotted, there are 115 field of views for the SDI, and so I broke them down into different quadrants based on their field of view, and I plotted them just to take a look at what the wind speeds are like. And you can see that there are strong winds as well as fairly fairly periodic wave activities with the zonal wind as well. Finally, while I had the data, I wanted to also do a comparison of the Rayleigh LiDAR and an AIRS comparison. And so the AIRS, oh, I didn't mean to do that. Go back, please. Now we will wait. There we go, perfect. So in order to do that, AIRS, which is this yellow line right here, has a resolution of about 10 kilometers. And so in order to make it a fair comparison, I took the blue line, which is the Rayleigh LiDAR, and I took a moving average over 10 kilometers. And that left me with this red line right here. So if you compare the yellow, which is the AIRS data, and the red line, which is the average LiDAR data, you can tell, although they're similar, AIRS is just not picking up those smaller perturbations lower in the atmosphere. And these are important because they can grow and deposit more momentum as they grow up into the atmosphere and create secondary waves into the thermosphere. So in conclusion, December 23rd was a night of high variability and a fairly strong wave presence in many regions of the atmosphere. The MERA-2 data showed that there is a polar night jet disruption in the upper stratosphere, as well as evidence showing that mountains were likely not a source to the gravity waves that we saw upward in the higher altitudes. We plan to continue our comparisons with the LiDAR to the AIRS data to look for evidence of small vertical wavelengths likely generated in the stratosphere. I'd also like to thank everyone that came to my poster on Tuesday night for comments, questions, and suggestions. And thank you.
Thank you very much, Sophie. We have time for a question. Anyone has a question at all? No question. I have one question. When you're looking at so with the AIRS, what do you think we can use as a better data set to look at the smaller scale things? And that?
I think it's tough because there's obviously a give and take. The LiDAR is only in one place, and so it doesn't give us that global view. I don't really have an answer on what we can do better to get those smaller scale perturbations, but I think it's just something to consider when looking at the scope of what project you're looking at, what research you're doing. Are those smaller scale perturbations important to consider?
Thank you very much.
Thank you.
Okay, we'll move on. Our next speaker is Katrina Bossert.
Hello. So I'm going to give a brief overview of using the GUVI FUV radiances to look at gravity waves and observe gravity waves. I'm also going to discuss some multi-instrument measurements. I want to acknowledge co-authors who recently were on a submitted paper that is currently under review. So on this plot, we've got a particular day. I chose a day in 2013 for the reason of comparing to the GOCE satellite, which was also in orbit at that time. 2013 was also a very interesting time. We had a sudden stratospheric warming. There was a lot of gravity wave activity. And what I've plotted here are 3 different emission lines from the GUVI data. Now, I will point out that these have been background subtracted, so we are seeing the residual perturbations here. These dotted lines denote the signal-to-noise ratio. And there's a different line for each of these different emissions. So we've got 1304, 1356, and LBHS. We did not have enough signal in LBHL to see these wave perturbations. And what we're seeing here is a perturbation along this track that appears to have a horizontal structure on the order of 2,000 or 2,500 kilometers. Now, another important aspect here of why this particular track was chosen for study is that it overlaps with some ground-based instrumentation at Poker Flat as well. And another thing to point out is that these emissions are coming from about 140 kilometers. Now, if we smooth these perturbations, what we'll see, so I've low pass filtered these and converted them to percent perturbations. These are a very large event. This is a particularly large event with percent perturbations ranging from about 2 to 4, maybe even 5% in some of these emissions. Now, the first question that I would ask myself is, well, is this real, or is there something a little bit odd with the way that the background was subtracted? And so the way that we would confirm that is to look at some other instruments. So here we have, the GUVI measurement, the pass was around between 22 and 23 UT on 18th of January. Well, we had some GOCE passes very close or very nearby a few hours before and a few hours after. And similarly, these both densities and cross-track winds are seeing perturbations on the order of around 2,000 kilometers. Another aspect here is that we have the poker flat incoherent scatter radar. When we look for longer periods, or what would be considered to be LSTIDs when observed in the poker flat incoherent scatter radar, we see persistent LSTIDs with periods of about 2 to 2.5 hours, all throughout this period of measurements. And also, while the GUVI measurements take place during the day, just for curiosity's sake, we can use the SDI 630 nanometer winds. So that's looking after sunset. We've got measurements here from about 2 to 6 UT, so overlapping this last portion. And we also see something in the SDI data, both at Toolik Lake and Poker Flat, with a period of somewhere between 2 and 2.5 hours. So we are seeing some large-scale waves present. So one of the questions here would be, where would these waves come from? And I think that's still a question that's up in the air because, as Sharon pointed out earlier, a lot of people have considered LSTIDs to come from the aurora, but we also know that they can come from below. And this day is interesting because these are fairly sizable waves with fairly significant perturbations. There is some activity, auroral activity. We are looking on the day side. This is also during a sudden stratospheric warming. So this is an interesting case, and I think there's still some research to be done as far as where a lot of these LSTIDs and large-scale gravity waves are coming from. So this is the work that we recently submitted, but I also want to touch upon something else here, which is, could we potentially use GUVI to look at some smaller scale waves? And I'm going to talk about something that's a little bit controversial. We know that GOLD also was able to measure waves recently. You can see the England 2021 paper, and they used 1356 and LBH to see a similar large-scale wave. But GUVI also has 1304 or 130.4 nanometer emissions. And this is a little complicated because while that is a much stronger signal, it's also a multi-scattering process. So we may have the advantage of being able to see wave perturbations, but we may not know exactly where they are coming from. We aren't looking at a specific pierce point. So I looked at a different day with a lot of MSTID activity. We also still had some LSTIDs present. So this is a day from a week or two before. And again, this was during one of the peaks in MSTID activity just before the SSW occurred. And as you can see, this is AIRS. There's some really strong regions of gravity wave perturbations. We have some strong perturbations and winds due to planetary wave disruptions of the polar vortex. And here is our unfiltered electron densities and our filtered electron densities showing a lot of MSTID activity. So what I did here is I subtracted, so these are the three different emissions. Again, I said I'm going to focus on the strongest emission, 1304, high pass filtered it. And so these are significantly smaller perturbations. Again, for that first event, it was an event we're pretty confident on, perturbations of even as high as 5%. We're looking at perturbations here that are maybe 0.5% to 1%. And so, are these real? And I think that's an interesting question that we can investigate more. But for a first glance at this, and just kind of a first CEDAR workshop study, what I've done is I've looked at a few passes around the globe on this particular day. And with some of the previous talks, we're going to see a trend that seems to match what other people have been seeing. So this is, again, AIR's data. So if you aren't familiar with that, we're looking about 35, 40 kilometers somewhere in the stratosphere. All of these are gravity wave perturbations. They seem to follow regions of stronger winds in the polar night jet. And then we also have less wave activity on this side. So what I've done is I've looked at and I'm almost done here. I've looked at the regions, I've looked at the strongest perturbation. I've compared that perturbation, done a running average of the perturbation over a distance. The blue line here is an SNR of 1. I just drew this dotted line for SNR of 3 for perturbation strength, just so you get a kind of a baseline comparison of the days. So we have 1 right here, some wave activity, but we are crossing with GUVI over this region of strongest wave activity. And that happens to be where we see the strongest perturbation strength in GUVI. And then over here in these quieter regions, we also see less strength here. So this is kind of indicating that we are able to see some of these smaller scale waves, or what would be considered MSTIDs, or waves propagating from below, in FUV radiances. So with that, I'll finish up. I want to point out there's still a lot of work to be done on this. And so, if you're interested, you can reach out to me or Larry Paxton, who's been working with me on this, but was not able to make it to CEDAR. And with that, I'll take questions.
Thank you very much, Katrina. Do you have any questions for Katrina at all? No, Sharon?
So on this period you're looking at, there were huge mountain waves over Alaska and over the Rocky Mountains as well. And so you could have polar vortex generated gravity waves as well as mountain waves, which go through the polar vortex and lengthen their lambda z, and then they break on top of it. So you could potentially have a complex sources of waves that then make secondary or higher order waves through the ways that we've been discussing. And so you could potentially, my question is, and this is the question I always have whenever it comes to this kind of thing, how can you separate these sources in the data? Is there any way? Do you think of anything?
With just one measurement, that's hard. But I think this is hitting on how we need multiple measurements at different altitudes, and of course, working with modelers as well to try and pull these things apart.
Okay, thank you very much. Our next speaker will be Asti Bhatt.
Hi, everyone. I hope this works. I'm going to talk today a little bit about what we have been observing in the newly established Mango Daisy network. And I'd like to acknowledge my co-investigators and co-authors here, Jonathan Makela and Brian Harding, Luis Navarro, who was postdoc with Jonathan Makela a couple of years ago, I guess. Many of you may know that sorry, I don't know what the pointer is. Okay. Oh, yeah, I should know. The original Mango network was established as a network of red line imagers across the continental United States, essentially to broaden our field of view of the nighttime ionospheric propagation processes. And this was done in 2014-2016 timeframe and has been operating since. This particular figure is part existing imagers and part artist conception of what the complete network may look like. In 2019, we proposed to create a new nested network of green line imagers and FPIs to go along with, so that we have similar view into the green line air glow processes. Oh, it works. The goal, the science objectives of the Mango Daisy network was to investigate vertical propagation of thermospheric variability, study the relative impact of lower atmospheric forcing with respect to magnetospheric forcing, and determine spatial scales of the lower and upper thermospheric winds. Much of this was inspired by what we had observed in the Mango red line imagers. These are some snapshots from a few events across the United States over the years, where you see the waves propagating in every which way, north, south, east, west, a combination of thereof. What happens when you put all of this sort of together? And this is a thing that you saw this morning Anthea show. Here, some thunderstorm activity going on down below here, and you see waves propagating north, northeast, and northwest from that source. Again, I want to emphasize, there's a point of clarification here. This is red line data. And then you will see what green line would look like in similar situation. So this is the current network. It looks a little bit different from the artist conception, but that is to be expected. We have this many red line imagers working, and some of these are being renegotiated as hardwares graduate and get obsolete. We have 4 green line imagers and 3 FPIs already established. As you can see here, this is a nice, in a coincidence, I should say, 3 green line imagers are on the same longitude, and they are the red line from the center location here covers all 3 imagers, field of view green line imagers, and the FPI. This imager here and FPI here are co-located with Christmas Valley Superdarn. So Luis Navarro has developed really nice visualization tools for both winds and the wave field from this green line network here. So let's see what that looks like. Again, you saw this a different day, I guess, in Anthea's presentation this morning. The green line air glow signatures here are much smaller scale than red line. So again, a point of clarification, the resolution here is a direct consequence of what green line altitude scale sizes look like. What surprised us a little bit is I don't think any of us really expected both the winds and the wave field to look so consistent across these large distances. And you can see the green line winds in both all the way to Oregon and here to Utah, they are consistent. The right side here is the actual wind directions. Another day. So, of course, there are clouds because we are optical imagers, so don't pay attention to this. Don't pay attention to this right away. But eventually, you will see that there is wave propagation activity going eastward in the southern part of this network, and then some wave activity going westward in the Utah imager here, while in the middle imager here, you can see both of them come together. I should point out that for this day, anyways, we did see some thunderstorm activity up above here that may explain the westward wave signatures, but this signature right here, the eastward going waves, we have seen it repeatedly over and over again, but we haven't been able to pinpoint a source that might cause that. We might have to look into the mountain waves or something. This is specifically for Sharon. So now we'll look at what we had originally sort of intended to do with this nested configuration. There is a lot of thunderstorm activity in this region, Gulf of Mexico and everywhere. So we have this one-day example here where there was this activity going on, thunderstorm activity on April 26th. And now we have data both from green and red line in this region. So let's see what that looks like. So this is data from red line up above here and green line down here, where you can see that there is wave propagation away from the source in green line and in red line, of course, with different wavelengths, different horizontal wavelengths. The winds are, red line winds and green line winds are also consistent with what we see in terms of the directions. So next, I want to show what we saw during the volcanic eruption that everybody has been talking about here. This day was actually near full moon day, and most of our imagers have no data because the moon was always there, except the imager in Utah, which is nestled at the Capitol Reef National Park with red rocks around it. So as the moon went below the red rocks, exactly, literally at that point, the wave arrived. And so we have this, we have this event which we'd never expected to see. So that is green line, and that is red line. And we see slightly different wave signatures in both, even though they're both going in the same direction. Pavel Inchin from Embry Riddle has done analysis of this and found that the horizontal wavelengths that you see here are between 80 to 90 kilometers, and in red line is from 150 to 200 kilometers. One thing to note here is that winds are, in the green line, winds do not look consistent with the wave direction that we have expected to see in typical gravity wave signatures. Red line, we don't know what's going on. We are looking into it. But so those are some of the examples I wanted to show. And in conclusion, I want to say that this imager network is partially done. We are still looking into having 5 more sites. Well, as many sites as I can possibly find. So if you know about any places in typically Western United States where they have a dark sky location, please reach out to me or Jonathan or Brian. Last CEDAR, we advertised this, and this is how we ended up with the Christmas Valley Superdarn site, thanks to Simon Shepard. But we are looking to establish more sites. As you saw in the beginning, the vision is to have 10 imager sites. So we also have, but even with whatever we have right now, we have a lot of data with clear examples of gravity waves signatures. There is a lot of data for neat research projects. If you're a student, you're looking for something to do with airflow. The raw data from existing network are available in near real time, and we are actively working on putting process data also available in near real time. It will be shortly available at mangonetwork.org. Finally, I want to thank NSF for supporting the Mango Daisy project for these 3 awards. Thank you.
Thank you very much, Asti. Do we have any questions for Asti at all? Yep.
there's something else going on.
Okay, we got one more quick question from Sharon here at the front.
So my question is, just in general, with the cases you showed, is it true in general that the phase speeds of the waves in the green line and then the red line are similar? And if so, no, they're not. And for the Tonga case, what was the phase speed of the waves in the red line that you saw for the hundreds of meters per second? And in the green line, what was the phase speed? Okay. In the green line as well? Is the green line sampling 95 kilometers, or is it in the thermosphere?
Thank you very much, Asti. And last but certainly not least, we have Nathaniel Frizzell.
Hi, everyone. Thank you very much. So today I'm going to talk about recent advances in observing traveling ionospheric disturbances using amateur radio techniques. So one question, of course, is what is amateur radio? It is a hobby for communicators, builders, and experimenters, and it's a wide-reaching demographic, all ages and walks of life, and it's particularly good for citizen science because these are people who are self-selecting to pursue some additional training and licensing, which involves knowing about basic electrical engineering and space weather and things like that. So from this, the reason we care about the amateur radio community here at CEDAR is because they often communicate using shortwave or high-frequency transmissions. So in this ray trace here, go back. In this ray trace here, you have a station transmitting in Florida on 14 megahertz. The signal can go up to the ionosphere and then be refracted back down to Earth where it's received by another station. And so you have the ionosphere can modulate this signal as it passes through. And so if you observe the received signal here, it's possible to do some remote sensing on the ionosphere. So because of this, I was able to start the Ham Radio Sciences Investigation, or HAMSci, which lets us professional researchers work with the amateur radio community to advance science. Now, when I was a graduate student working in SuperDARN, I looked at medium-scale traveling ionospheric disturbances, MSTIDs, and this is a ray trace simulation I did during my PhD. And you can see here, you get, let me do that one more time. What you can see here is I've perturbed the IRI with a traveling ionospheric disturbance that would move from north to south. This is a Fort Hayes radar, and these structures can actually focus and defocus the radio waves, and it will cause the skip distance to move in and out in range for the radar. So if you look at the ground scatter signature, you can see these wave structures. So I wanted to know, can we see these same sorts of structures in amateur radio communications? And there are at least 3 networks that automatically observe amateur radio communications, and these are built by the amateur radio community for amateur radio purposes, but they make their data available publicly. And so they have kind of a worldwide, very heavy on US and Europe though, observations of the amateur radio communications, and they go back to 2008. Very nice data set. So I took data from all three of those data sets from November 3rd, 2017. I looked just over the United States, and I plotted the data so that the y-axis is going from 500 kilometers to 2,500 kilometers in range between transmitter and receiver. And then we're looking at 12 hours of time on the x-axis. And right here you can see an oscillation in the inner skip distance. And so you can actually fit a nice 2.5-hour sinusoid right to the bottom of there. And that matches very well with the SuperDAR and radar observations from the Blackstone SuperDAR and radar, which is looking right over this area. So that's a period that's consistent with a large-scale traveling ionospheric disturbance. I also looked at differential GPS total electron content from the MIT Haystack Observatory, and you can see here a wave front there, a wavefront here, and there's a trough. And I was able to take a box around there, and I just calculated the median differential TEC there, and you get this nice oscillation, which also has a 2.5-hour period, which matches very well with the amateur radio and the SuperDAR observations. So here's all three of those observations stacked up nicely. Same period wave seen in all three data sets. And here you can actually, here's a movie. When you get more TEC, that's going to be more refraction on the HF amateur radio signal, so you expect the skip distance to go short. And when you have a blue region like this, less TEC, the ionosphere is weaker, you expect less refraction, it goes long. So if you watch this movie, you can see the US turn red when the skip distance comes in and turn bluer as the skip distance moves out. And you see these nice wave structures moving southeast across the United States. So we can take the amateur radio data and we can slice it into little latitudinal slices going down here, and you can identify peaks in the wave right here, and you can watch those progress in time, and you can estimate a phase velocity from that. And here are the estimated parameters I got from this data, 2.5 hours for the period, 1,100 to 1,200 kilometers. That should be kilometers per hour, I believe. Phase velocity, horizontal wavelength, about 1,600 kilometers, propagating to the southeast. So I looked at some high latitude sources for what might be causing this, and there was auroral activity in the supermag electrojet index, and then also, let's see, enhanced electron densities and Joule heating from Pfizer about 3 hours before the TID observed in the amateur radio data. And I did a number of estimates projecting that back, and it does line up well in terms of time in this region where supermag suggests that there was the enhanced auroral activity. So it's very probable that this particular event was caused by a gravity wave generated by Joule heating from the electrojet. So this has recently been published in GRL, so you can go read all of the details of that event there. And what it does is this provides a basis for doing future statistical studies on this. So I've already had my student Diego Sanchez manually go through a year's worth of data and create a climatology of when these LSTIDs are occurring in the amateur radio data set. You can see they occur more in January, February, and October, November, December in the United States, and less in the summertime. And so you get this interesting seasonal distribution, which actually matches very well with the climatology I published in 2014 looking at SuperDAR and MSTIDs. And so this is perhaps a little surprising if everything's generated by auroral activity, that you would see this sort of seasonal dependence. So, one of the things we're doing right now is trying to work out why we would see a similar seasonal dependence here, even if it's generated by auroral geomagnetic activity. So this was done manually. We're also developing a machine learning approach. Bill Engelke from the University of Alabama has done this, and he's going to be talking about this in the afternoon 4 p.m. session, Pedrina's TID session. And so he now can go through this amateur radio data, have his machine learning algorithm automatically detect the TIDs, and he can also generate climatologies. And so far, those climatologies are similar to the ones that Diego has been finding manually. So we're going to continue working on this, trying to make sure our climatologies are actually correct, and then trying to interpret them properly. Thank you.
Thank you very much, Nathaniel. Do we have any questions at all? Oh, Sharon?
Very nice talk. It's really exciting. Can you get MSTID? So I have two questions. Can you get MSTIDs from this amateur radio, the bottom side? Okay, go ahead.
So the way we're doing it right now, we can see some signatures of it, but the data set's very noisy, so I'm very hesitant to say that I could do a really robust MSTID analysis with this right now. Okay. Maybe in the future we will be able to. I can also say with our personal space weather station project and the grape receivers, I do believe we will be able to see MSTIDs in there.
Cool. And if you go back to your slide where you compared your Blackstone data with your amateur radio data, the Blackstone, that was daytime, right? That was daytime events only, or was that day and nighttime? And also with amateur radio, is that day and nighttime?
So the Super Darn MSTIDs is daytime only. Because the ground scatter tends to go away at night. The amateur radio, we can usually get daytime on 14 megahertz and nighttime on 7 megahertz. So we have the opportunity for seeing both, but at different frequencies. Yes, so you could probably say that the green bars are likely daytime and the orange bars are likely nighttime.
Yeah, I have a comment and a question.
Sure.
Scientific question. My comment is that to the conveners, if I think in the discussion, if somebody is referred by name, they should get an opportunity to reply to the question or the criticism. That's one comment. And my scientific question is, under quiet times, geomagnetically, and let's say solar quiet times, do you think observationally, one can see signatures of wave generation by Joule heating or in general ion neutral interactions? Because we always have plasma flowing, and they do their own thing, and then you have the neutrals.
I will just say that I believe that under geomagnetically quiet periods, we can see TID signatures. What is exactly causing them right now, I'm not going to conjecture that much right now. Cool. But we can see these during geomagnetically quiet periods. We also, Diego's work so far has suggested that there is some slight geomagnetic enhancement when we do see the more TIDs. We see a little bit of a correlation there, but we're still working on getting that right. We'll just see where things come out. I think there might be some possibility that there's some filtering that's going on. We'll have to work on that.
Okay, thank you very much again, Nathaniel. And I'd like to thank all of the speakers again, and all of you for your participation in this workshop as well. And off to lunch.